You're gonna tell us something.
So is this it's the title? So can we just
Yeah.
just start from where we left off last time? Or
Yeah, sure.
okay.
Yeah, this is all that we're going to be discussing static electricity for the next few weeks. So I'm continuing the story here.
Benjamin.
Troy.
Are we skipping Haskeby or coming back to him later?
Oh, yeah, I decided to skip him actually because I told you that Otto von Guericke invented this machine where he could spin big glass balls around really fast and rub things against them and get more static electricity than people had in the past. Well, he didn't really publicize that discovery, and so people had to rediscover it. And the guy who rediscovered it in England was Hawksby. But since I already told you about that discovery in connection with von Guericke, I'm going to skip Hawksby.
So he didn't do anything else besides invent that?
He did some other things, but he investigated some interesting electrical phenomena that turned out to be too complicated for him to really figure out what was going on. I mean, he was a smart experimentalist, but he just tackled too hard a problem, and so he got stuck.
Something that we learned?
It's well, I can tell you a little bit about it now. What Hawksby did, the guy that we're not going to talk about, he noticed that if you had a glass tube of mercury, say, that was, and you shook it up, you would see, I mean, after you had rubbed the glass and made it electrical, and then you shook it up, you would see strange lights around where the mercury rubbed against the glass. And he particularly noticed that he could get even more of that light that he would see if he pumped some of the air out of the tube. So if the air was a partial vacuum, and then he rubbed the glass and shook it up with the mercury in it, he would see these strange lights. Well, it turns out that's kind of a complicated phenomenon. And so it was, he worked on it for a while trying to figure out what was going on and never really figured it out. But later scientists would eventually figure it out. Okay, but the guy who made the really key discovery that was going to lead to a whole bunch of further discoveries and some key new ideas in electricity was the main guy I want to talk about today, which was Stephen Gray. And Gray was, he got interested in electricity in the 1720s. And at the end of the 1720s, in 1729, he was doing an experiment, and he noticed something peculiar. He had been rubbing these glass tubes in order to get static electricity for the experiments that he was doing. Well, it occurred to him to wonder whether or not if he closed the glass tubes, if he put pieces of cork in the ends to close the tube, whether that would affect the electricity, whether he'd get more electricity or less. Well, turns out that it didn't affect the amount of electricity that he got by rubbing the glass tube. But he noticed that when he put the cork at the end of the tube and rubbed it, that the cork became electrical. He hadn't rubbed the cork. So, I mean, this was the first time that, that people had noticed that something they hadn't rubbed became electrical. That there seemed to be a transfer of electricity from the glass tube to the cork. Well, what's the next thing you would think of doing? Put yourself in Gray's shoes here for a minute. Okay, he's just stuffed this cork in the end of the glass and noticed that the electricity seems to go from the glass to the cork. Selah, what would you do next?
Touch it?
Hmm?
Touch it?
Oh, touch the... that's not what he thought of doing next, I don't think. Now, if you do that, you will de-electrify it, right? What would you? That's not what you would expect it to happen if you touch it. Okay, yeah, that is what happens, and Gray found that out. But Gray thought of doing something else. Evan.
Rubbing the cork and seeing if it electrified or made the glass.
Oh. Well, see now, Gray's that wasn't what got Gray excited about this experiment. See, he thought, okay, I can rub one thing and have the electricity transfer to something else. Drew.
But what if you let's say you touch the cork, would it be repelled from the glass or would it just be de-electrified?
Oh, well, if you once you electrify the object, if you touch it, okay, the electricity will run off. Okay, I mean it'll de-electrify it. Okay, so they knew that at this point. Now, Troy, you got an idea of what you would do next?
Well, he could make a line of objects to an electroscope and electrify one at one end and see if it can make the electroscope.
Yeah, you're on the right track. See, what Gray thought was, well, this cork is directly touching the glass. What if I instead hook up something? The first thing he thought of was, okay, now, I mean, if the cork is directly touching the glass, it gets electrified. What if I stick an iron wire into the end of the cork and then attach an ivory ball to the end of that wire? Okay, now the first thing he did, he had a 6-inch long wire with a ball attached to it that he stuck into the cork. Now he rubs his glass and sees, well, what happens to the ivory ball at the end of the wire now? Drew.
Doesn't it spark?
Well, I mean, it gets electrified, is what he found. Okay, so now the electricity is going from the glass to the cork, through the wire, and finally to this ivory ball. Tom.
What made him think that the electricity would go through a wire?
Oh,
Why not use, say, a thread?
That was pure luck at that point. Wire just happened to be the thing he had laying around in the laboratory at that moment. We'll see in a minute that he doesn't understand there's anything special about wire. It was just a way he had of connecting the ball to the cork. So the next thing he tries, at this point, he's curious as to how far he can extend this distance. Okay, so what he does next is he takes a piece of pack thread instead of wire, and he hooks the ivory ball, ties the ivory ball to that, and then attaches that to the cork. But now he's got like a 3-foot line of thread rather than his little 6-inch wire. Okay, rubs the glass tube, and the ball at the end of the thread charges up. Okay, so now he's shown that it'll go through a 3-foot length of damp pack thread. Yeah, Ben.
So for the first example, not only does the wire get charged, the ivory gets charged.
Yeah, right. That's what he's testing, is the ivory. He's holding up, say, an electroscope, something, to this ivory ball.
Yeah.
Or he's holding the ivory ball up to an electroscope and seeing whether it'll attract, seeing whether the ball is charging up.
Yeah.
Nick?
Was it also a coincidence that the thread was damp?
Well, it was fortunate for Gray. Now, it's not really a coincidence because things are always damp in England, and he's in London. So it turns out actually that Gray ends up doing a lot of experiments with this pack thread, and I mean he's in London and it's always really damp there, and so his thread was always damp. Well, when people in drier climates tried to repeat some of these experiments, they had some trouble. And they eventually figured that out. Yes, Drew.
Did the wire also become charged, or was it just the ivory ball?
The wire would become charged too. Yeah. Okay, so now he's shown that it will go through this 3-foot length of thread. So the next move is pretty obvious. He takes 30-foot length of thread and stands up on his roof. And so he can just hang it vertically down to the ground where his assistant has this electroscope and can see whether the ball will attract the electroscope. Rubs the glass tube, and it works. Okay, so the electricity is going from this glass tube into the cork, and all the way through this 30-foot length of damp pack thread into the little ball he has tied to the end. Drew.
Does it matter how hard you rub it, or you just like go like that and then it'll roll?
Yeah, it matters. I mean, you have to get good contact between the whatever you're using, piece of wool cloth or whatever, and the glass. So, rubbing it hard for a while will work better than just taking a few swipes at it. Yeah, Ben.
So is the tube open on one side, or is it open like?
Oh, well, it turned out it doesn't really matter. I mean, whether he corks both ends or just corks the one end. I mean, he found out that whether the tube is open or closed doesn't make any difference.
Yeah.
Now, okay, so what can he do next? I mean, his roof is only so high. So 30 feet is about what he's limited to in terms of vertical distance. Selah.
So he uses a longer string and goes to a cliff or something? I don't know.
Well, no, he decides to, there weren't any nearby cliffs, I don't think, that were handy. So what he decided to do was he would just string this thread of his horizontally. So now, I mean, he just wants to see how long he can make this thing and still have it work. So he starts, so here's his glass tube with his cork in it. And here's Gray himself with his cat that he's rubbing against it. Um, and he's got this thread. Now, he figures he'll just, well, he started out using just hammering nails into a horizontal beam that he had on wherever he is in his garage or part of this this structure of his house. So he's got this these long horizontal beams along the side of his house, and he hammers nails into them, and then just ties the thread around these nails, and so he can get a long piece of thread just winding it around his house, say. Now, he found that this didn't work. So, I mean, after you do this, you know, he's got this long piece of thread, and then he's got this whole thing attached to, say, an ivory ball here. And then here's his electroscope, okay? And the ivory ball has no effect on the electroscope in this case. Nick, what's happened?
As the hammers, the electricity is being diverted to the nails.
Exactly. That's what Gray figured. Is the electricity is escaping into these nails, so that it's not making it to the ivory ball. So Gray thought about that, and he thought, well, how can I prevent that from happening? Daniel.
Is the big clock tower in London around? So couldn't he try and go vertical again?
Oh, he was actually he was outside of London in the country when he was doing these experiments. So, right. If he had been in London, he could have hung something vertically for more than 30 feet. But he's stuck with some kind of. It actually turns out to be a good thing that he had to go horizontal here, because he learned some very important things when he did this. Troy.
You can't cover the nails in a material, cover the thread in a material.
What would you cover the nails with?
Rubber.
Rubber. Yeah, but you know things that Gray doesn't know. So that's not fair. I mean, remember, at this point, you know, people didn't know much about electricity. Now, Gray had an idea, actually. Yeah, Salem.
Metal nails, right?
Hmm?
They wear metal nails?
Yeah, metal nails.
Why didn't he, well, wooden ones work?
Well, now, if you think about it, at this point in people's knowledge, why wouldn't Gray have used metal nails? I mean, if anything, he would have thought that there would have been an advantage to using metal nails, because Gilbert had metals listed as non-electrics. I mean, if you rub a metal, you can't charge it up, Gilbert found. I mean, you can give me a chunk of metal, and I'll, you know, take my cat and rub the cat against it and then hold it up to the electroscope. Nothing happens. So Gilbert had classified metals as non-electrics. So you would think, well, if metals, you know, don't respond to electricity, then it seems like this should have worked. But it didn't. And Daniel?
Could you cover it with cloth, maybe?
Well, here was Gray's idea. These were pretty thick nails that he had used. So he thought, well, maybe the reason the electricity is able to escape into these nails is because they're thick. I should just try something really thin. Okay, well, he happened to have some very thin silk cord around. So he thought, okay, here's what I'm going to do. Rather than attaching this damp pack thread to the nails, I'm going to attach it to little pieces of this silk, really thin silk cord, and then see what happens. Okay, well, what happens when he did that, Drew? It works, absolutely. So these attachments here, experiment 1, with nails, failed. So he switches to thin silk cord. Success. Okay? Which means that the ivory ball charges up and the electroscope moves. Now, it occurred to Gray, though, that he should test this idea. When he saw that it was successful, okay, that seems to be evidence for his idea that he needed something really thin here, that the electricity couldn't escape through. Drew?
You should try thinner nails.
Yeah, well, that's in effect what he did. It occurred to him, well, I should test and make sure whether the thinness is really the issue here. So he had some very thin brass wire. And so he decided to try that. Okay, so forget the iron nails, but replace the thin silk cord with equally thin brass wire and see what happens in that case. Okay, what happens? Fail. Right. So So now Gray realizes that what's important here is not the thickness or thinness, is the material. Silk works, and iron and brass don't. Okay, but now he's caught on to how we can make this thing work anyway. So, if he just uses the silk cords, he can rub the glass here and charge up the ivory ball over there. And he's still interested in pursuing this question of how long this connection can be and still have this ivory ball charge up. So he goes around his place and he sticks poles in the ground and puts hooks on them with little silk cords. And he strings his damp pack thread, all over the place. And he gets up to a length of about 700 feet. And when he rubs the glass tube, the ivory ball charges up and the electroscope moves. Yeah, Ben.
Doesn't this come to like the power lines?
Yeah, exactly. Exactly.
Is he the one who found out that it powers like, well, you can power like contraptions, like machines?
Oh, well, he didn't get that far. Because they haven't found any real use for electricity yet. But this is the first ancestor of the modern power lines. We go out today and you see poles stuck in the ground everywhere with these big wires attached to them. And we don't use pack thread, but they found that wires work better. But this is the first aerial transmission line that Gray made. It just carried a little bit of electricity over about 700 feet, but that's where the idea came from. Yeah, Drew.
Did you ever try, like, if like you had one string, maybe taking like another string, connecting it to that one, and having it split off like that, and having two balls to see if they would power the other ones?
No, I don't think he did that. At least I don't remember reading about it. That would have been a good thing to do. Yeah, Troy.
Did he ever use the glass ball instead to make more electricity?
Oh. Later, other people did. Gray actually didn't have one of those electrical generators at his place, so he was stuck with the rubbing.
Was the charge weaker than it was with like 3 feet or something?
Oh, no, not noticeably. It's I mean, this pack thread is really thin, so it doesn't take much of the charge itself. So you end up, I mean, Gray didn't notice really any dependence on the strength of the charge on the length of the line. So he showed it could go through 700 feet anyway. It's pretty good. Okay, now notice that what Gray has got here is a oh, by the way, there is one other thing, variation that Gray did on this experiment that was interesting. He didn't always use an ivory ball here. He replaced this ball with a number of different materials. And one of the things that he tried using instead of ivory was metal, various metals. Now, what do you think? Do you think anything different happened when he used metal? Troy.
Maybe the charge a little stronger? Or?
Not noticeably. Basically, the metals behaved just like the ivory. So he could charge up metal here, where now that would have surprised him a little bit, because remember that Gilbert had classified metals as non-electrics. I mean, he couldn't rub them and get them to charge up and move an electroscope. Well, here, Gray doesn't have any problem getting the metal to charge up and the electroscope to move. So what's different? Why didn't it work when Gilbert tried it, and it does work when Gray tries it? Nick?
Because it's not being rubbed. Maybe it can't be charged up when it's being rubbed, isn't it?
Well, that's partially true, but why? There's something about what Gilbert was doing that's different than what Gray is doing here. Yeah, Ben.
Gilbert was just rubbing them together, but Gray was feeding power to the ball. So then
Well, it does make a difference. I mean, Gray was never touching, when he had a metal ball here, he never touched it at all. Okay.
When he was touching the metal, it was running back onto himself.
Exactly. Yeah, that's it. That's why it never worked when Gilbert tried it, because he was holding the piece of metal and rubbing it, and then this is what Gray actually realized this, that when Gilbert had tried this, the electricity had run off into him. So that's why it hadn't stayed on the metal. Yeah, Drew.
Was the metal that he used, the wire, was it damp also, or?
Oh no, it doesn't have to be damp. I haven't told you yet why the pack thread works a lot better when it's damp, but I will in a minute. Daniel.
Now, why is it that it would only work with metal, that the electricity would run back onto him, and not like glass or later on PVC pipe for us?
Right. that gets exactly at the point that, that I was going to get to next, and that Gray realizes at this point. Gray realizes there are two different kinds of materials. There are materials through which electricity moves easily, and then there are other materials where the electricity just doesn't move around. It gets stuck, basically. Okay? It doesn't move through these materials. Now, I mean, the perfect example of this, of the two different kinds, is the nails, okay, where he couldn't get the electricity to go to the ball because the electricity kept disappearing into the nails, versus the silk cord. See, he wasn't losing electricity into the silk cord. So electricity won't pass through silk, but it will pass through nails. So Gilbert introduces for the first time this basic conceptual distinction between two different kinds of materials. Materials that are called conductors of electricity, where the electricity passes through them easily, and materials that are non-conductors or insulators.
Wait, did you say electricity passes through metal, but not silk?
Right, right. So let's, let me see. Gilbert, or excuse me, Gray, makes this distinction between conductors of electricity versus insulators. Now, based on the experiments that I just described to you, we would put iron over here under conductors, brass, what else?
Ivory.
Yeah, right, that pack thread that he used.
Yeah.
Right, I should add that.
Ivory.
Excuse me?
Ivory.
Oh, no, it will, remember that insulators can have electricity on them, but will, I mean, to prove that ivory, for instance, is a conductor, you would have to show that, say, if you had a long piece of it and you touched a charged object to one end, that it passed through it to the other end. So he hasn't really shown that. He's just shown that he can get charge on this little ball. But he would add to this list people. Selah.
What about the other materials you use for a ball? Because you said that you use like metal and stuff to substitute the ivory ball. Would that work?
When he substituted metal for the ivory ball, the metal got charged up.
Like what kind of metals?
Oh, any metal, yeah. So basically, what he eventually finds is that it's not just iron or brass, that actually, well, I'll just put it down here on the list. Any metal is found to conduct electricity. Now, insulators, silk, yeah, let me see. He hasn't proven that, but I'm pretty sure that ivory is, in fact, an insulator. Glass.
Cork.
Yeah, Drew.
How can you really test test glass to see if it would work.
Oh,
You really couldn't get like, unless you had a really long glass piece of.
Get like a sheet of glass and attach a wire to one end and another wire to the other.
right, right. If you had a big sheet of glass and say
Wire connected to another, and then you charge.
right, if you had put a charge object against one end of it and see whether you can pick up charge on the other end. Or
Well,
something.
not only that, like if you
Right.
had like a piece of glass here, then you connect wire to that side, and then you had the wire go to another piece of glass, and you charge that one glass, and see if it would travel through the wire and charge up that one glass, the glass on the other end.
Right.
Would that also be testing?
Yeah. So you could. I mean, there's anytime you can get electricity to travel through a piece of material, relatively easily, then Gray is going to put it into this category of conductor, and if he can't, it's an insulator. Now, obviously, all these things are. It's not that these things are perfect conductors and these things are perfect insulators. There's a degree here, but and the very best conductors were found to be the metals, but there is a clear distinction. Troy.
So after Gray, does anybody call things electrics or no?
Well, that's right. Good question. These are actually the concepts that came to replace the ideas that Gilbert started with. Remember, Gilbert classified materials into electrics versus non-electrics, right? Now, how are those ideas related to these? Troy.
Well, non-electrics would usually be the conductors and the insulators would be electrics.
Yeah, exactly. That what Gilbert called the non-electrics, Gray now realizes that, well, they're just conductors. And the only reason that Gilbert couldn't electrify them was because the electricity was running off them into him, because he's a conductor. Okay, so the electricity was disappearing. But in fact, if all you have to do is take any of these materials that Gilbert called non-electrics, let's say a piece of brass, and if you insulate it, say tie it hang it with a piece of silk, and then touch charged objects to it, there's no problem in getting the brass to electrify the brass, to get it to be electrically charged. So that these so-called non-electrics are not, there's no problem. You can electrify any object, Gray realized. It's just that if it's a conductor, you have to insulate it, otherwise the electricity will run away. Drew.
When he was rubbing the glass, when he was testing his theory, was he touching the glass or was he going like that, just touching the thing?
Oh, he would, yeah, I'm sure that he wasn't touching the glass because, I mean, you can actually charge up something that doesn't conduct. You can charge it up even though you are touching it, because it won't move from this part of the electricity on this part of the glass tube won't move to the other side of the tube and run into you. So
Yet it runs into the cork.
yeah, the cork, I mean, I don't know what the conductivity of the cork is, but
It doesn't run into your hand from the glass, but it runs from the glass to the cork.
so, oh,
It must just run a little bit.
yeah, that's a good point. Because that's what initially tipped him off. I wonder.
It's not conducting from the glass. Because the end of the glass is charged, and that's pushing the charges through the wire.
Pushing the charges to the cork, though.
In the cork, yeah. Into the wire. The glass doesn't conduct into the wire. I don't think.
Oh, but I mean, he noticed that the cork seemed charged even when he didn't have a wire in it. But it's, I see, it's electric, okay. Yeah, I see. The effect for the cork is actually a little different. We're going to talk about the cork isn't getting, it's not so much that the cork is on the end of the glass is getting charged as it is this other effect called electrification by influence that I'm going to tell you about in a minute. Okay, but yeah, Troy.
Would cork be a conductor or an insulator?
So cork would be an insulator. Okay, so notice a couple of things. I mean, first we started out with the electricity being this strange attractive property of a particular material, amber. Now, Gray has proved that everything can be electrified. It's just that if it's the kind of material that electricity runs through easily, then you have to make sure to insulate it and not let the electricity get away. But assuming you do that, you can electrify any object. And notice what Gray, this discovery of Gray's. Electricity has already come a long way from the initial, from what the Greeks knew about it. I mean, if you went to Thales, okay, in 600 BC, you told him, okay, Thales, you've got this big backyard. Here's what you do. Go out there and stick poles in the ground all over your yard. And then put hooks in them and take little silk threads and tie them to the hooks and then string all this thread or wire all over your yard and see whether you can rub this piece of amber and get this ball on the end of the string to charge up. He would have thought you were crazy. So, yeah, Ben.
Aren't people already charged? Like,
Aren't what?
people already like charged electrically?
No, we're not.
Cause like, I watched a couple of videos about like your mind and stuff, and I see all the electrical things going around or something.
No, it's not that we have a constant electric charge on us, though, that we're electrified. It's, you certainly can electrify people. In fact, Gray did this. That's the next experiment that I wanted to tell you about. Gray took a young boy. I'm not making this up, and he suspended him on silk, using silk cords. And then he would charge up his glass tube and touch it to the boy's feet, okay, the bare feet. And he did this a few times. And then he would hold his electroscope up to the boy's face, the nose. And sure enough, boy's nose attracts the electroscope. The book I have that describes this didn't say where Gray got the boy or whether he was a volunteer. Troy.
If you had rubber gloves on and then rubbed a piece of metal and then held up to an electroscope, would it attract it?
Yeah.
Yeah.
Yeah. Drew.
Can you also use wood?
Oh, I'm going in. I just completely forgot about the time. We'll save the wood question for next time. And continue with this next time.